Hello everybody and welcome along. My name is Neil Moore and I am the Product Manager at Harwin for EMC boardware and industrial connectors. In today's presentation we will look at the development of through-hole and surface mount technology and the differences in their assembly process. We will consider the pros and cons of using each type of connector, why you may choose one over the other, and what this means for both your circuit design and the manufacturing assembly process. And finally, we shall look at the pin-in-paste or pin-in-hole reflow process, what this is and what you need to consider when making your connector selection. Initially, there was a single process for the soldering of components onto a circuit board. The leads or legs of a component were inserted through a hole drilled through a printed circuit board before an operator would manually solder these legs in place, forming the electrical connection. In order to speed up this assembly process, it was automated with the introduction of wave soldering. This allowed for one side of the circuit board to be populated with components. As only one side of the circuit board was being populated, the real estate required to house these boards was massive in comparison to today's standards. As consumers demanded more functionality from their electronics without compromising on their size, more space needed to be found on the circuit board for the additional components that would be required. This led to the development of surface mount technology and surface mount design. By not requiring holes to be drilled through the circuit board, which were needed for the traditional through-hole components, the real estate on both sides of the circuit board could now be utilised and populated with components. However, without component legs protruding through to the bottom side of the PCB, a new form of soldering needed to be developed. The solution, Reflow soldering. This enabled the development of higher technology devices in smaller packages. So let's look at the automated soldering processes so that we can understand what each means for our component selection. Through-hole components will have legs, leads or pins on their underside. These are what are inserted through the copper-plated through-hole in the printed circuit board. Although the types of plated holes in PCB design are numerous, from small mechanically drilled via holes of 0.2 or 0.3 mm in diameter, used to make a connection from the top to the bottom side of the circuit board, to laser drilled blind and buried vias of 0.1 mm, used to make connections between one layer of your multi-layer PCB and its direct neighbouring layers. A connector's plated hole has the same goal, to make a connection from one area of your PCB to another, in this case remote point. The through hole required to accept a component such as a connector will be larger in diameter, say between 0.5 and 4 mm. The size of the hole will typically depend on the connector's current carrying capability. The higher the current, the larger the connector lead and the hole size required. The traditional method of soldering through-hole connectors to the PCB would be wave soldering. So let's take a look. Once the PCB has had its through-hole component mounted, it is loaded onto a wave solder line. The first process is to spray a flux coating on the underside of the PCB. The flux is only applied to the bottom side where the through-hole component legs or terminals will be presented. The board then moves into a preheat stage which activates the flux coating. Flux, when heated, acts as a cleaning agent to ensure that the metal surface of the circuit board pads and the component leads will be clean and free of contaminants. The board then passes over a wave of molten solder which makes a connection between the PCB and the legs of the through-hole component. Finally, the board is then cooled to solidify the solder joint between the copper pads and the component lead. This form of wave soldering can be used for PCBs that contain only through-hole components or a mix of surface mount and through-hole components. In this case, surface mount components would be soldered first in a reflow oven before the through-hole components are mounted and the board is passed through the wave soldering process. For wave soldering, components are present on the top side of the PCB and the solder joint is formed on the bottom side. The surface mount connector will not have the same leads as a through-hole connector. Instead, the leads will be splayed out horizontally and rest onto the pads on the surface of the PCB. In reflow soldering, a solder paste is screen printed onto these PCB pads via a custom designed stencil. This incorporates cutouts that match the pad positions. The size of these cutouts will be designed to consider the thickness of the stencil material being used and the type of solder paste being used. Solder paste comes in a variety of forms with a mix of different metal and flux content. This will form the soldered joint once processed. During reflow soldering, up to 50% of the solder paste volume printed onto the pad may be lost at the flux cleaning stage. It is therefore important to consider how much paste you need to apply, considering the contents of the solder paste, the size of the cutouts in the stencil, and the material thickness of the stencil itself. For single-sided assembly, solder paste is applied to the top side, side A of the PCB, where the component will be mounted. In high volume production, surface mount components are also mounted onto these pads using pick-and-place machines. Due to the tacky nature of the solder paste, the component will be held in position prior to being passed to the reflow oven for soldering. Let's take a look. The reflow oven contains several zones which one after another will raise and lower the temperature that the PCB and components will experience. The initial stage is the preheat. This slowly raises the temperature of both the PCB and the components, careful to prevent any damage occurring as a result of a sudden thermal shock. The next stage is the soak. During this stage, the flux element of the solder paste is activated, the flux acting as a cleaning agent that removes oxides that may have naturally built up on the component legs and the PCB pads following manufacture. As you can see, the temperature within the reflow oven is increasing at each stage. Following the soak, the temperature in the next zone increases to its peak value, and this is where the reflow of the metal elements within the solder paste occurs. The solder element liquefies and makes the connection between the component and the circuit board. The PCB and the component are only held at the peak temperature for a very short period of time before passing into the final cooling stage to bring the temperature back down. With the introduction of the restriction of hazardous substance legislation in Europe, resulting in the removal of lead from the soldering process, different lead-free plating finishes and solders were introduced. However, it was found that most required higher processing temperatures than their lead-based predecessors, which raised the topic of lead-free soldering and determining both PCB and component materials suitable to withstand the higher processing temperatures. So now we have taken a look at the different assembly processes. What does this mean for my circuit design and which soldering process will be used? Well, does my circuit board require components to be present on one side or both sides of the PCB, and what types of components and connectors can be used? Traditionally, a circuit board requiring only single-sided assembly would be made up exclusively of through-hole or surface mount components. Each of these would require either a single wave or a single reflow soldering process. However, as we saw previously with the requirement for more technical capability in smaller forms, as common in higher-end electronics, a mix of component types will be employed and require multiple soldering processes. But how many? Here we can see all of the traditional stages of the component assembly process laid out, but which do we need? Remembering that there are costs associated with each step. If we have a circuit board exclusively with through-hole or surface mount components, we can see that we can pass through one soldering process only. However, as previously discussed, this is less and less typical of today's assembly requirements. If we require a mix of through-hole and surface mount components on one side of the PCB, as can be seen on line 3 here, then we would typically require two soldering processes. One reflow process for the surface mount and one wave or selective for the through-hole components. Initially, the surface mount components would be soldered using the reflow process, and then the board would be loaded onto the wave solder line. If there are only a limited amount of through-hole components, we may replace the full wave solder with a selective soldering process instead. This is similar to the wave soldering process, except a smaller, localized fountain of solder is raised at the required position only, rather than the whole bottom side of the PCB being passed through the wave of molten solder. All components would be present on the top side of the PCB, therefore a single-sided assembly. If you wish to take advantage of all the freed up real estate on the bottom side of the PCB, you would need to populate both sides using SMT components. There are a couple of ways this can be achieved. The initial top side of the PCB is printed with a high temperature solder paste and the components are mounted. The PCB would be passed through the reflow oven before being rotated and the bottom side being printed with a lower temperature solder paste. Components are then positioned on this side and the PCB is again passed through the reflow oven. The difference in solder paste activation temperatures prevents the components on side A from reflowing again and falling off of the PCB. If the components are of significant size and weight, they may be held in place with the use of an additional bonding agent. This is known as a double-sided reflow. There may be an additional wave or selective soldering process to assemble larger through-hole components to the PCB, as we saw previously. We often see component manufacturers offering both surface mount and through-hole versions of the same parts. But why? What are some of the considerations that would lead us to choose one type over the other? Let's look at some of the pros and cons of surface mount technology. The pros. The main benefit of using surface mount technology is that you have removed the holes present on the bottom side of the circuit board and freed up this space for the additional components to be added. The cons. The component fixture strength. Surface mount components are only mechanically attached to the PCB via the copper pad on which they are soldered. A copper pad itself is only retained onto the PCB by the bonding between it and the material below its surface area. Therefore, the pull force resistance or peel strength is much lower than that of a through-hole connector. The component material suitability. We have to consider the materials which the components are produced from. The whole component body will experience the high temperatures associated with passing through a reflow oven, unlike just the legs or leads being soldered from below. Therefore, it is important that the component body be able to withstand these temperatures. The component materials should also be considered to help reduce the potential for outgassing, where when heated, trapped gases within the component material may escape, leading to the potential for solder voids or inconsistent wetting of solder joints. The process setup and ongoing maintenance. As we have seen, the setup for correct volume of solder paste needs to be calculated. The size and the shape of the component pads versus the stencil aperture and the type of solder paste type to be used need to be considered. There are some guidelines in the IPC industry standard 7527 relating to the volume and alignment of paste on pads. There are ongoing production considerations also. The solder paste stencil needs to be cleaned on a regular basis between applications to prevent the build-up of paste within the aperture in order to ensure correct application. Within the reflow assembly process, it is important that the size, variation and position of components are considered when setting the temperature profile. This is in order to ensure that the temperature of the PCB and the components follow a linear profile. Solder wicking may occur if there is a wide variation in the temperature gradients, with the component legs heating faster than the PCB copper pads, resulting in the solder flowing up the component leg and leaving the PCB contact pad bare and without a solder joint being formed. Through-hole technology and processing. The pros. This is a long-established method of component assembly and well known. It comes with the added benefit of increased mechanical fixture strength compared to surface mount technology. The cons. The main drawback of through-hole technology is it restricts space on the opposite side of the PCB for additional component placement. It also requires a separate assembly process which has added material costs such as the solder bar, separate flux chemistry and processing time. In an ideal world, we would like to populate both sides of the PCB but with the benefits of a through-hole component's mechanical strength, but avoiding the processing time and expense of having to run an additional soldering process. So how can we achieve this? Well, let's look at paste-in-hole reflow, or pin-in-paste as it's sometimes known. First developed in the mid-80s, pin-in-paste is a relatively new assembly process in comparison to the traditional wave soldering or reflow ovens. Its aim is to be able to solder both through-hole and surface mount components during the same reflow soldering process, thus removing the time and cost associated with the additional wave solder. In the process, solder paste is printed across both the surface mount pads and the through-hole pads on the top side of the PCB. The surface mount components are placed onto the PCB as before, and the through-hole components are pushed through the solder paste colouring their holes. The PCB would then be passed through a reflow oven and all solder joints would be formed at the same time. So you may be thinking to yourself, pin-in-paste really does look like the best of both worlds. Well, let's have a look at the pros and cons of it. The pros. We've removed the need for a separate wave soldering process in the assembly. Therefore, we've reduced cost of capital equipment and processing times. We reduced the number of thermal cycles that our board will be exposed to. As we know, thermal cycling can introduce component fatigue. The more cycles, the more fatigue. We also reduce handling between separate processes. Handling introduces the opportunity for error and damage to the board. The cons. The process setup. In addition to the previously discussed setup considerations for surface mount components, we have now introduced another factor when considering the solder paste application. When a through-hole component is pushed through its hole, the paste printed over the hole will be dislodged in an uncontrolled manner. Therefore, we need to consider printing an increased volume of solder paste over these holes to compensate. This may require some adjustment to our solder paste stencil or a change to our circuit design to increase the annular ring size around these holes. Solder preforms may also be a consideration, however this has to be balanced against the cost of these as well as the processing time to fit them. Not all traditional through-hole components may be suitable for the pin-in-paste reflow process. Typically, larger connectors would not be suitable without the addition of a bonding agent to help hold the component in place. And in high pin count components, there may be thermal variations, resulting in some pads wetting more successfully than others. When making a component selection for pin-in-paste reflow, it should also be considered that the body material used in some traditional through-hole components may not be suitable for reflow oven temperatures, for the same reasons as we looked at before. Also, traditional through-hole components will typically have longer leads or legs, which may displace more of the solder paste printed over the through-hole when inserted. The typical amount of solder paste displaced is believed to be proportional to the length of the lead. Components designed for use with pin-in-paste process may have shorter lead lengths to counter this problem. However, it should be considered that there is an IPC industry requirement for a minimum lead length of 60 mm that must be present on the bottom side of the PCB to ensure a sufficient solder joint. When deciding if pin-in-paste is an option for your assembly process, you would weigh up the setup considerations versus the processing time and material cost savings to be made. If you or your assembly partner already have wave or selective soldering operations in place, you may not look at the pin-in-paste option. After all, you have already purchased the capital equipment and have a good process in place to optimize efficiency. If you don't have this, then pin-in-place may be an option for you. So what does this look like? Here we will look at the requirements for single-sided assembly. Initially, solder paste would be printed onto the surface mount components and over the through holes on the top side of the PCB. The surface mount components would then be populated onto these pads using your auto mount pick and place machines. Through-hole components would then be inserted through their holes, before the complete assembly would be submitted to the reflow oven for soldering. Finally, the assembled board would be inspected. Using this process, you have removed the handling stage and also a production step. Let's look at how this would work if you had a double-sided assembly. Initially, solder paste would be printed onto the surface mount pads on side A of the PCB using a higher temperature solder paste. These pads are then populated with components by the pick and place machines. The PCB is then passed through the reflow oven, soldering side A. The PCB would then be turned or flipped to present side B as the top side. Solder paste would then be printed onto the surface mount pads and across the through holes. The surface mount components would then be placed as before using pick and place machines. The through hole components would be inserted and the PCB would be passed through the reflow oven once again. Finally, the board would be inspected. Again, you have removed a handling process as well as a manufacturing process. To summarise, today we have looked at through-hole components, how they are traditionally assembled using wave soldering, and what the positive and negatives are of this style of connector. We have seen that they offer greater mechanical strength compared to surface mount components, but at the loss of real estate on the opposite side of the circuit board. We have looked at surface mount components, understood their benefits, but seen some of the considerations in their assembly setup. Finally, we have looked at a possible solution in pin-in-paste that gives the mechanical strength where needed, but also the efficiency and material savings compared to operating separate assembly processes. I hope that you found today's presentation informative, and if you have any questions relating to Harwin's ranges of through-hole or surface mount connectors, or indeed any of our PCB hardware components, please feel free to get in touch with me. Thank you for your time and enjoy the rest of your day.